Hi again, this is the fifth in a series of 5 videos on row reduction, and in this video we are going to discuss the number of solutions that a system of linear equations can have. Earlier we solved a system of equations and found exactly one solution, which is written here, and you see 3 numbers, so you might think this would be 3 solutions, but keep in mind this is just telling us one particular way of assigning values to each variable. -11 for x, 7 for y, and 0 for z. So we think of this as just one solution. However, not every system of linear equations has exactly one solution. So you might ask, can a system of linear equations have exactly 2 solutions? It turns out that the answer is no. So we'll see why this is true, and more generally, we're going to answer the question, what are the possibilities? How many solutions can a system of linear equations have? To begin with, it's going to help to adopt a graphical perspective. For example, let's say we want to determine whether or not the point 1, 4 lies on the graph of the equation 2x plus 3y equals 6. We can do this without actually drawing the graph. All we need to do is plug the point into the equation. So 1 gets plugged in for x and 4 gets plugged in for y, and the result here would be 2 times 1 is 2, plus 3 times 4 is 12, and that's 2 plus 12, which is 14, not 6. And that just tells us the point does not lie on the graph. If plugging in a point's coordinates results in a true equation, then the point does lie on the graph. So let's practice this with an example. Does the point 4, 3 lie on the graph of the equation 7x plus 5y equals 35? Let's see. So we'll plug 4 in for x, and then we'll plug 3 in for y, and what do we get? Well, we want to know if that's equal to 35. Let's see. 7 times 4 is 28, and 5 times 3 is 15, and 28 plus 15 is 43, which is not 35. So the point does not lie on the graph. In summary, the graph of an equation consists exactly of those points whose coordinates make the equation true. Now we can combine what we know about solutions with what we know about graphs. Earlier we called -11, 7, 0 a solution to our first system of equations because when we substituted those values in for the variables, each equation was made true, or in other words, was satisfied. Similarly, the point 3, 6 is a solution to the system x plus y equals 9 and 2x minus y equals 0. We can check that real quickly just by substituting in the values, 3 in for x and then 6 in for y, and we find that 3 plus 6 is equal to 9. And similarly, 2 times 3 minus 6 is equal to 0. So, in summary, what we have is that a solution is a point that satisfies each equation, which in graphical terms means it's a point that lies on the graph of each equation. In other words, in the picture you see here, the solution is the intersection point of the two lines. Now we're ready to answer our original question, which was, how many solutions can a linear system have? For example, let's say we're given equations for two lines. In that case, the number of solutions is just the number of points where the lines intersect. At this point, I would recommend getting out some paper and trying to draw graphs that show 3 different ways lines can intersect or fail to intersect. And if you're going to try this, you'll want to pause the video to give yourself enough time. Okay, let's take a look at the first case you might have come up with, which is the unique solution case. This is the one that we saw earlier where there is exactly one point that lies on both lines. And because there's just one point, that point's special, and we call it unique. The next case is maybe a little less obvious, but there was a hint. Remember, we said the lines could fail to intersect. So how would that happen? They could have the same steepness or slope. In that case, since they don't intersect, there are no points on both lines, and we have no solution. What about the third case? This is probably the least obvious, but let's see. Okay, here we have both lines lying on top of each other. In other words, not only do they have the same slope, but they're actually the same line. So that means that any point on either line will have to be on both lines, and therefore there will be infinitely many solutions. Or we say the solution is infinite. Although these pictures only represent the two variable case, x and y, a linear system will always have either no solution at all, exactly one solution, or infinitely many solutions, even with more than two variables. Now we can shift from the graphical perspective back to the algebraic perspective. So let's say you are performing row reduction and you want to know how can you determine the number of solutions from the augmented matrix once it's reduced. Well, if there's a unique solution, it will be right in front of you, just like when we solved our first system. Let's take a look at an example in case you don't remember how that looks. Here we have a reduced matrix, which is what we get at the end of the row reduction process. And once we get that matrix, the next step is always to convert to a system of equations. The first row here represents the equation 1 times x equals 7, or in other words, x equals 7. And similarly, the second row represents the equation y equals -2, and the third row represents the equation z equals 5. So the solution is just right in front of us. We know automatically as soon as we convert back to a system of equations that x is 7, y is -2, and z is 5. So there's just one solution, which we can write as an ordered triple, 7, -2, 5. If it's not clear why this is one solution instead of 3 solutions, let's think about that. It helps to think of 7, -2, 5 as a single point in 3-dimensional space, which just looks something like this, where we have an x, a y, and a z-axis. Just like an ordered pair xy represents a single point in the xy plane. How will we know if a system of linear equations has no solution? As always, we begin by reducing the augmented matrix and converting back to equations. Let's see how this looks in an example. Here we have our reduced matrix, and when we convert the first row back to an equation, we get x equals 7, and the second row gets converted to y equals -2. And what equation would correspond to the third row? Well, we know that 0 times any number is equal to 0, so 0 times x, no matter what it represents, is just 0. And similarly, 0 times y is 0, and 0 times z is 0. And therefore, the left-hand side of the third equation will be 0x plus 0y plus 0z, which is just 0. And the right-hand side is 1. So the third row is telling us that 0 is equal to 1, which is a bit strange. So let's see how we can make sense out of this. Since there are no values for x, y, and z that make the equation 0 equals 1 true, the other two equations don't matter. It's impossible for all three equations to be satisfied, so the system has no solution. Now, there is another way to look at this. It's true that whenever there is no solution, we will get the equation 0 equals 1. Basically, if the system has no solution, then as long as the augmented matrix has been completely reduced, it will always contain a row corresponding to 0 equals 1. In practice, however, it's not always necessary to fully reduce the augmented matrix when a system has no solution. For example, if the augmented matrix contains a row corresponding to 0 equals 5, we can conclude that the given system has no solution at that point without continuing to reduce, because there are no values of x, y, and z that satisfy 0 equals 5. Lastly, we have the infinite solution case. And how will we know if a system of linear equations has infinitely many solutions? As usual, let's take a look at an example. First of all, is this matrix reduced? Well, let's see. We have our leading one in the first row, and its column is clear. And we have our leading one in the second row, and its column is clear. And we have our leading one in the third row, and its column is clear. And also we have a nice staircase. So this matrix is reduced. And using the variables r, s, t, u, and v, what equations correspond to this matrix? Let's see. The first row gives us r plus s plus 4u equals 2. The second row gives us t plus 3u equals 1. And the third row gives us v equals 0. How can we be sure, though, that there are infinitely many solutions for this matrix? Well, we know there must be at least one solution because the matrix is reduced and we don't see 0 equals 1. Also, we don't immediately see a unique solution, and this tells us the solution is not unique. So there must be infinitely many. Great, we know there are infinitely many solutions, but there's more. Just one piece of the puzzle remains. We still have to actually find the general solution. And here's how we're going to do that. You first just identify the columns to the left of the rightmost column. In other words, we're only interested in the columns that correspond to variables, not the column that represents what goes on the other side of the equal sign. So looking at those left columns, we want to find the ones that do not contain a leading 1. And we're going to use the word parameter to refer to each of the variables that correspond to these columns. The next step is just to move the parameters to the other side of each equation. Let's see how this looks in our example. Well, first of all, where are our leading ones? They're here, here, and here. And remember, step 1 said we want to identify the columns on the left part of the matrix that do not contain a leading 1. Those would be the second column and the fourth column. And what do we get when we convert back to equations? Just what we had before, except that now we've singled out columns 2 and 4, which correspond to the variables s and u, and we know that those variables are going to be what we call our parameters. The next step is to move the parameters over to the other side of the equation. What I mean by that is, in the case of the first equation, we want to subtract s from both sides so that we have just a minus s on the right hand side. And similarly with the 4u, we'll subtract that from both sides. And then in the second equation, we want to move the 3u over by subtracting it, and this is what we get. And in the third equation, there are no parameters, so we don't need to move them over. Okay, and that is our general solution. This is one way to write it. But what does that mean? Although there are infinitely many solutions, that does not mean that we can always obtain a solution by just arbitrarily choosing numbers for each variable. We can, however, arbitrarily choose numbers for the parameters s and u. That's why these variables get a special name, and we call them parameters. For example, let's just choose two numbers randomly, say 1 for s and 2 for u. But we could really just choose any numbers, -7 and 1/2, for example. But let's say we choose these two, s equals 1 and u equals 2. In that case, our equations tell us that r would have to be 2 minus 1 minus 4 times 2, because we just substitute our values for s and u. And so r has to be -7. And similarly, substituting in 2 for u into the equation for t tells us that t has to be -5. And then we obtain a solution which gives us the values of each variable. -7 for r, 1, which we just randomly chose for s, -5 for t, and 2, which we randomly chose for u, and 0 for v because we know that v always has to be 0. In this way, we have the ability to generate infinitely many solutions because we can make infinitely many different choices for s and u, and each different choice will produce a different solution. When you need to carefully express your answer to a system of linear equations that has infinitely many solutions, or maybe choose an answer on a multiple choice test, you have a variety of options, and different teachers will tend to follow different conventions, but a few of them are listed here. In the first case, we have just listed the same equations that we had at the end of our last example, and then we just specify at the end that s and u are arbitrary. Another way to say the same thing is, again, to just list out the equations, but this time you include the equation s equals s and the equation u equals u. Since s equals s is satisfied no matter what number you plug in for s, this is another way of saying that s is arbitrary. The third option requires you to know something called set builder notation, and I won't get into the details here because it's not essential to understanding how to solve these systems. It's just that if your teacher wants you to know it, this is another way to write your answer. You would just list out the right-hand side of each of the equations from the second option in an ordered quintuple, and then specify again that s and u can be any real number. That's what this symbol means here. Alright, we now know how to solve any system of linear equations in any number of variables. That's quite an accomplishment, and all that is left on the road to mastery is practice. Thank you so much for working through these notes, and if you found them helpful or have a suggestion, please leave a comment to let me know.